Hello, my name is Mr. Asbury and I'm really excited today to bring you a MadAsMaths question paper. This is Mathematics MP2, it's practice paper D, and it's based on the EDEXCEL Pure syllabus. And I would say that it's aimed at students who are looking for an A to A star. They're really tricky questions. They're great to do because it kind of puts you a little bit out of your comfort zone and you have to really work on your problem solving skills. This guy is fantastic. He made all these papers. They are freely available on his website. Link is in the description. Make sure you check it out. Let's do it. So we have f of x is equal to 1 minus x to the power of a third. It says find the binomial expansion in the ascending powers of x up to the x squared term. Okay, so that's fairly standard. It means we're going to be using the formula which you're given your formula booklet, and that's going to tell us that f of x is equal to 1 plus nx, where n is the power and x is, well, the variable inside the bracket, which in this case is minus x, and then it's plus n minus 1 x squared over 2 factorial. And we don't need to go any further than that because we've just been asked for the x squared term. So simplifying this gives me 1 minus a third x, and this is going to give me 9 on bottom. The two 2's will cancel out there. There'll be a negative. Those negatives will cancel out there. So it'll be negative 1 over 9 x squared. Okay, so that's part A. And this will be part B. Okay, so now we've got g of x, and we need to use the result in part A. So that means we have to do it to get the marks, essentially. And then we need to work out g of x expansion up to the x squared term. Well, let's see how g of x and f of x relate. So g of x is equal to, well, I could pull that 8 out of the bracket, and when I do that, I need to take the power with it. And that will give me a 1 inside the bracket as my numerical term, which is what we're looking for in order to use this formula. And I'll have to divide that by 8 as well. So this is a way of writing g of x. So 8 to the power of a third is 2. So it looks like this. And then this is very similar to f of x. Well, it's 2 lots of f of x if the x was changed to a free x over 8. So if I just replace the x there with a free over 8, then we get the same function as f of x. Okay, so we can do this then. All we need to do is just times our expansion for f of x by 2 and replace all the x's with 3x over 8. So I'm going to get 2 lots of 1 minus a third times by 3x over 8 minus a ninth times by 3x over 8 squared. Okay, so this is 1, 3's will cancel, so that's minus x over 8, and here we'll get 3 squared on top, which will cancel with the 9 on bottom, and we'll have to square the 8 on bottom as well, so that'll be 1 over 64 x squared. Okay, so times that through by 2, we get 2 minus x over 4, and that will be minus x squared over 32. Perfect. Okay, let me grab some more space and we'll do part C. Okay, part C, it says, hence show that the cube root of 7 is approximately equal to this. Okay, well, if we look at g of x here, we could quite easily get 7 inside our bracket if we select a certain x value. So if we let x equal a third, which we're allowed to do because x needs to be in between these two, and which a third is, then that will give me that on the left hand side we'll have 8 minus 3 times a third, which is just 1 to the power of 3, is approximately equal to this side here, which is 2 minus, okay, if x is a third, then x over 4 is a 12th, and if x is a third, then that means a ninth, and 9 times 32 is 288. Yes, that's right. I'm trying to do this all without a calculator, just for practice. So this gives me the cube root of 7, which is exactly what we're trying to estimate. And here we would get 576 over 288, and that's 12 times 20, 24, so minus 24. So all in all, that gives me the correct amount. Yeah, it does. 551 over 288. Maybe I will use a calculator in future questions. Okay, question number 2. It says x is measured in radians. Use small approximations to simplify the following expression. Okay, well, cos squared is the same as 1 minus sine squared. So the first thing I'm going to do is I'm going to substitute in like this. But I don't need a bracket here. And the reason why is because the small approximation for sine squared, for sine, is much easier than the one for cos. And that's minus 1 there. And that's all over 2x sine 3 over 4x. Because sine theta is approximately theta, tan theta is approximately theta, but cosine of theta is approximately 1 minus theta squared over 2. So you can see how the sine is much easier to use sine, basically. Okay, so how does this simplify? Well, this also knocks out the 1's on top, which is nice and helpful. So we just have here, we have negative sine, which is just theta, but in this case it's 3x and then squared, so 3x squared, and then over, this is 2x, and sine of 3 over 4x is just 3 over 4x. Okay, great. Let's simplify this. So that's on top is minus 9x squared. And down here we're going to have 2 times 3 is 6, and 6 over 4 is the same as 3 over 2. So 3 over 2 x squared. Maybe I don't write it like that. Maybe I write it a bit neater. So 3 like over 2 like that. And then we can simplify this because we're dividing by that, so it's the same as flipping this over. So timesing by 2 and dividing by 3x squared gives me minus 18x squared over 3x squared. X squareds will cancel. Minus 18 over 3 is minus 6. Beautiful. Okay, next question, and we've got a summation. We've been asked to sum up to 12 starting at 1 of this set of terms. So what we can do, we can split them up, and that's exactly what I'm going to do. I'm going to first sum 2r up to 12 starting at r equals 1. And a good way of doing that is just writing out a few terms just to see what on earth is going on. So when r is 1, we'll get 2, because 2 times 1 is 2. And then we'll get, when r is 2, we'll get 4, and then we'll get 6, and then we'll get 8, and then we'll get all the way up to the last one, which will be 2 times 12, which is 24. Okay, now it's fairly obvious to see here this is an arithmetic sequence. It has a start term 2, it has a common difference of 2, and it has a number of terms of 12. So we can use our formula for the summation of the arithmetic, which is it's n over 2, so 12 over 2, times by 2a, so 2 times 2, plus n minus 1, which is 11, times by d. So that's the summation formula, which is in your formula booklet, but you should remember it really from GCSE. So that's 4 plus 22 is 26, times by 6, which is 120 plus 36, so it's 156. Okay, good. Now what we need to do is we need to do the next one, which is going to be the summation of 7. Okay. In hindsight, I could have added that onto the first one, but I didn't. I overlooked that. But anyway, the summation of 7 just means for every value for r, it doesn't stay, it just stays constant. So it's just going to be 7 plus 7 plus 7 plus 7 12 times. So that's simple, that's just 7 times 12, which is 84. Okay, and now for the last one, the summation of 2 to the r. Okay, well once again, I'm just going to use the method of just writing out a few terms and just see what's going on. So when r is 1, we get 2. When r is 2, we get 4. And then we get 8. And then we get 16. And then we get all the way up to 2 to the 12, which I don't know. Okay, but anyway, this is an arithmetic sequence. Sorry, it's a geometric sequence with start term 2, a common ratio where we're timesing by 2 each time, so the common ratio is 2, and again the number of terms is 12. So the formula for the for the geometric is a, open brackets, 1 minus r to the power n, all over 1 minus r, which is just 1 minus 2. Okay, right. I think this is where my non-calculator is going to come to the end. Okay, and we got an answer of 8190. Okay, so our total answer will be all of these underlined ones added together. So that is 156 plus 84 plus 8190, and voila, that is a total of 8430. So we are cooking. That is good to go. Bosh. Okay, next question. Use the trapezium rule with 5 equally spaced ordinates to estimate the value of the following integral. Okay, so if there were 5 values, 1, 2, 3, 4, 5, then it means there's going to be 1, 2, 3, 4 strips. Okay, so that means that the height of my trapezia will be 18 minus 2 over 4, which is 16 over 4, which is 4. Okay, so what I'm going to need is I'm going to need a table whereby let's call, well, we'll have x, and we will have the first one will be at 2, and then at 6, and then at 10, 14, and 18. And we'll have a y value for each of those. And what we can do is we can use our table function on our calculator, so that's what the calculator is there for. So we can go to a table function, and we can type that function in, which is it's ln of 2 over the square root of 4 plus the square root of x. There it is. Oops. Okay. And then close all those brackets up. Press equals. We don't need the second function. We're going to start at 2. We're going to end at 18, and we're going to go up in steps of 4. Okay, great. So there's all our numbers. So minus 0.151, minus 0.238, minus 0.291, minus 0.33, and then finally minus 0.361. Fantastic. Right, thank you, Mr. Calculator. You can go away now. Okay, so the trapezium rule tells us that our integral is approximately equal to the height, which is 4 over 2, and then the two endpoints added together, plus 2 lots of all of the middle ones added together. And I'm going to run out of space. How annoying. Let's just do that. Okay, great. So we can do that, and I won't bore you with typing that into the calculator. I'll just tell you what the answer is. There we go. We get minus 4.467. Okay, great. Right, let's move on to part B now. So part B asks us to estimate the integral of this, but using my answer to that last one. Okay, so we can write that the integral between 18 and 2 of ln of, and this is a division, so when we subtract 2 lns, it's the same as dividing the inputs of that ln there, so we can do 2 minus ln of 4 plus root x, all rooted means to the power of a half. Okay, and we knew that that was approximately equal to minus 4.467. Okay, now what we can do is we can split up these integrals. So I can put a little integral sign in here, because when you integrate one function, it's the same as integrating the two separate if they are split up by subtraction or division. Okay, so then we can rearrange this so that we make this bit here the subject. So that will be the integral between 18 and 2 of ln of 4 plus root x to the half is approximately equal to the integral between 18 and 2 of ln 2 plus 4.469. Okay, great. And now, okay, so what we can do is this power of a half here, we know from log rules that if we have the input raised to a power, that can come down to the front to be the coefficient. So I can bring that down to become the coefficient there. And then we also know that when we integrate, we can factorise out a constant, so that can go outside of our integral like this. Okay, lovely. Right, so we've got pretty much what we need. We just need to, we've only got half of it, so we'll just double at the end. Okay, so what is this? Well, when I integrate ln 2 is just a number, so it's just a constant, so it integrates to ln 2x, like that, between 18 and 2. And then when I evaluate this, first I'll sub in 18, and I'll get 18 lots of ln 2, and then minus, I'll sub in 2, so I'll get 2 lots of ln 2, like that, which gives me a total of 16 lots of ln 2, plus 4.469. Now, like I said, that was equal to this integral here, but I needed to I need to multiply it by 2, won't I? So put that in brackets and times by 2, and that will get rid of the half over here. Okay, great. So that just goes into our calculator, and we can get a value. Okay, and this is equal to 31.1. And I've just realised that I've been writing down the wrong number every time. That must be infuriating for everyone. I'm so sorry. That was a 7. So this needs to be a 7. This needs to be a 7. So this needs to be a 7. This needs to be a 7. And that needs to be a 7. And that gives us 31.1. Bosh. Okay, vectors. Love a good vectors question. And this one looks very good. So what I'm going to do is I'm going to start by drawing a diagram, because I think that is really helpful in questions like this. So I've got the origin, and I know point A. So that means I know the position vector of A, so I know the vector O to A. I know the vector B to A, which would look like this. I know that vector, and we're talking about M being the midpoint of OB, so that would be right here, and it says find the distance A to M. Okay, right, so to get started I'll need to find O to B. So O to B is, well, how do I get from O to B? I can go to A, and then I can take away B to A, because we're going in the wrong direction there, so I'm going to have to take away this vector. So essentially it is O to A minus B to A. O to A being the vector 6 minus 4, 1, the position vector of A, minus B to A, which is 1, minus 1, and 3. So this gives me a vector of 5, minus 3, and minus 2. Okay, great. Yes, that's O to B. So now we can find O to M, which is the midpoint of O to B, so it's half of O to B. So it's just this halved, so it is 2.5, minus 1.5, and minus 1. Perfect. Okay, so now I can find A to M, which is O to M minus O to A. So that is 2.5 minus 1.5 minus 1 minus O to A, which is 6 minus 4, 1. And that gives me a value of minus 3.5, 2.5, and minus 2. So then finally I'll just need to find the magnitude of A to M. So we'll do that by square rooting all of these components squared. So 3.5 squared, it doesn't matter about the sign because we're taking the square of them, plus 2 squared. And I'll do that on my calculator, and that'll give me 3 over 2 root 10. So that tells me that K is equal to 3 over 2. And that question is done. Okay, the simplest looking question on the paper, but the one I think is the hardest one to explain. So not massively looking forward to this question, but I'll give it my best go. Okay, so we've got the functions f and g, and it's just simply asked find the domain and range of g of f of x. So just so we're clear, g of f of x means I put x into f, and then I put that into g. So let's start off with what x's I can put into f. Well, the x's I'm allowed to put into f, well, because of the domain of f, is just anything which is less than or equal to 4. Okay, so I can put that into f. And what comes out then, so what values of f of x will come out if I put in values of x which are less than or equal to 4? Well, f of x tells me I need to double and plus 3, so doubling and plus 3 to 4 gives me 11, which means that f of x will always be less than or equal to 11. I'm then going to put those numbers into g. So that's me putting them into f, this is me putting them into g. Now the numbers I'm allowed to put into g are all numbers greater than or equal to 1. So at the moment I'm going to be putting in numbers into g which are less than or equal to 11. But I need another restriction. I need them to be only greater than or equal to 1. So that means that these numbers f of x that are going to go into g need to start at 1. So therefore, what x values, when I put them into f, give me 1? Well, f is, of course, 2x plus 3. So if I want it to equal 1, that tells me that x must be minus 1. Which means that x originally needs to be bounded so that it's greater than or equal to minus 1. So that bounding there gives this bounding here, which then allows g to be satisfied for greater than or equal to 1. Okay, so this is our domain. So we found that now. The domain of g of f of x is minus 1 between x is between minus 1 and 4. Okay, so now what about the range? Well, these are the numbers we're allowed to put into g. So what is that going to give us? Well, it's a quadratic, so it's a good idea to sketch the diagram. So we're allowed to put in x values up to, from 1 to 11. Well, when I put in 11, g tells me to square a minus 4. So that's 121 minus 4. So that's 117 all the way up here. And when I put in 1, well, that's 1 squared is 1, minus 4 is minus 3. So minus 3, let's say down here. Okay. Now, it may go like this, in which actually it goes lower than minus 3. Or it may just keep rising from minus 3 upwards, up like that, in which case it's between minus 3 and 117. Well, how do we know which one it does? Well, we know it has roots at 2 and minus 2, and in fact it means that the minimum point is actually going to be here at minus 4, so it's going to be symmetrical. So then it's going to start coming upwards. It's going to hit here at minus 3, and then it's going to keep on going up to 117. So all in all, that means that g of f of x, the range will be minus 3 up to 117. So I can write that the range of g of f of x is that g of f of x is bounded between 117 and lower bound of minus 3. Okay, job done. Question 7, and we have a beautiful looking question. I love questions like this, so simple. Okay, so I've been completely converted into doing questions like this where we need to convert between different trig functions by using just a simple right angle triangle. It's the most efficient way of doing it. It's just beautiful. Okay, so what you do is you put your angle in there, and because we know sine x is 12 over 13, sine is the opposite over the hypotenuse, we can then do Pythagoras' theorem to find the other side, and that will give me 5. Okay, the next thing I'm going to do is a quick cast diagram. So cast diagram tells me that all trig functions in the first quadrant are positive. Only sine is positive there, only tan is positive there, only cosine is positive there. Okay, so where are we looking? Well, we're in an obtuse angle. So this is between 0 and 90, and this is between 90 and 180. So we're in this quadrant here, which means sine is positive, but it means the other ones are not. Okay, well, let's find the other ones. That could be helpful. Cos of x, well, looking at this triangle, cos is the adjacent over the hypotenuse, and we know that it's negative because it's in the second quadrant. So it's minus 5 over 13. And tan of x, well, that is the opposite over the adjacent. And again, because we're in this quadrant, tan is negative, so it is minus 12 over 5. Okay, great. Right, now what do we need to do? Now we need to start thinking about the fact that they're asking us for cot. And in fact, they're asking us for cot 2 theta. Cot 2x, sorry. Okay, so what is cot? Well, cot is the reciprocal of tan. So it'd be great if we could find tan 2x. That would really help us on our way. Well, we know the double angle formula for tan. It's in your formula booklet. Well, at least you can derive it from your formula booklet. And it is 2 tan x over 1 minus tan squared x. Okay, great. So tan 2x is equal to 2 lots of tan x, which we know is minus 12 over 5, all over 1 minus 12 over 5 squared. Okay, lovely. So let's expand out. So the top gives us minus 24 over 5. And the bottom gives us 1 minus 144 over 25. Okay, times each term by 25 to simplify will give us, that will cancel a 5, times by another 5, minus 120. This will give me 25 for this term here, and this one will be minus 144. Great. So this is minus 120 over minus 119. Okay, so of course that's just equal to 120 over 119. So from there, because cot 2x is equal to the reciprocal of tan 2x, that means that cot 2x is equal to 119 over 120. Beautiful question, love that. Okay, question number 8 looks like a bit of a beast. It says that the figure shows 5 circles touching externally whose centers lie on a straight line of length L. The radii of these circles form a geometric progression where the radius of the smaller circle is 3 units. Okay, and the one of the larger one is 48. Okay, so that means that A1, the first term, has a radius of 3, and A5, the fifth circle or term, has a radius of 48. Okay, and we know that the fifth term in a geometric sequence is the first term multiplied by r to the 4, so n minus 1, which is 5 minus 1, which is 4. So this tells me that 48 is equal to 3 times r minus r to the 4. So r to the 4 is 48 divided by 3, which is 16, which means that r is equal to 2. Okay, that's good. The pattern is extended by 5 more circles to 10 circles. Determine the new length of L. Okay, so what is L? Well, L is all of the diameters. So it's 2 times the radius. And all of the radii form a geometric summation which sums up to the 10th term, starting at the first term, of the of the radii, basically. Okay, so we need to do 2 times by the formula for the summation, which is a, the first term, 3, times 1 minus r, which is 2, to the power of number of terms, which is 10, all over 1 minus r. Okay, good. So this is, well, I could just put this to my calculator and tell you what it is. Okay, so we get 6138. Lovely. Okay, then it says, calculate in terms of pi the total area of the 10 circles in the new pattern. Okay, that is tricky. Okay, so if you've got a series question, because it's obviously a series question, and you're finding it tricky, then the best thing to do is just to write out the first few terms to see if you can spot the pattern. So the first area will be, so the total area will be the first area, which will just be 3 squared pi, because the radius is 3. And then the next one, the radius is times by 2, because remember r was 2. So it will be 3 times 2 squared pi. And the next one, the radius is times by 2 squared. And then you square the radius, times it by pi. And that pattern will continue, so that the next one would be 3 times 2 cubed squared pi. Okay, now if I were to expand this out, each term will contain a 3 squared pi. So 3 squared pi, 3 squared pi, 3 squared pi. So we can factorize that out of our summation. Obviously there's going to be lots more. I haven't put ... because I've run out of space. But anyway, this is just getting an idea of what we're doing here. So 3 squared pi can come out. So the first term will just be 1 after factorizing. The next one will be 2, but that has to be squared because it's a squared there. Plus the next one will be 2 squared squared, so that's 2 to the 4. And the next one will be 2 cubed squared, which will be 2 to the 6. And obviously that will all go on until the last term. And the last term will be 2 to the 9 squared, which will be 2 to the 18. Yes, because the first one we don't times by 2, and then everyone afterwards we do times by 2. So there's going to be, the last one will be times by 2 9 times, and then obviously you square, so there's 18. Okay, so this is 9 pi, and this is a summation. This is a summation with first term, so a equal 1, and the common ratio, we're timesing each one by 2 to the 2, which is 4. So each time we're timesing by 2 to the 2 inside this bracket. Okay, so we can do the summation formula for that, which is a, which is 1, so we don't need to write that. 1 minus r to the number of terms, of which there are 10 terms, all over 1 minus r. Okay, perfect. So again, that can go into our calculator. Okay, and that summation gives us this. Then we have to times that by 9 pi as well, and that gives me 3145725 pi. And that was a fantastic question. Okay, next one. and we have a curve which is x equals in terms of y, and it says show that dy by dx equals. Okay, so I'm going to start by just differentiating with respect to y, because it's just set up perfectly for that. Well, what's that going to give me? Okay, so sec squared differentiated. So if we have sec squared, then we can use the chain rule. So the 2 comes down to the front. We keep the bracket the same. We drop the power down by 1, so sec to the 1, and then we multiply by the derivative of the bracket, and the derivative of sec is sec tan. Okay, great. And then tan, that's just your standard, differentiates to sec squared. That's one you should know. And we have this. Okay, and this is going to be 2 sec squared y tan y plus sec squared y. We can factorize out a sec squared here. Always good to factorize when you can. And then we can rewrite this because sec is 1 over cos, so we can write it as 1 over cos, which means we can put it at the bottom of the fraction in terms of cos. So over cos squared y. And then all's left to do is take the reciprocal of both sides, and that will give me dy by dx. So that is equal to cos squared y over 2 tan y plus 1. And that is what they've asked for. Perfect. Okay, hence show that the equation of the normal to C at that particular point where y is equal to pi over 4 is given like that. Okay, well, we've got the gradient function, so all we need to do really is substitute in to the gradient function to find the gradient. So dy by dx at y equals pi over 4 is going to give us well, cos of pi over 4 is 1 over root 2, and that will need to be squared, over tan of pi over 4 is 1, so times by 2 and then plus 1. Okay, so this is a half over 3, which is the same as a sixth. So the normal gradient is the negative reciprocal of the tangent gradient, so that will be minus 6. Okay, so we still need to know what the x-coordinate is when y is equal to pi over 4. So when y equals pi over 4, we have x equals, so subbing into the original equation, sec squared is 1 over cos of pi over 4, which is 1 over root 2 squared, plus tan of pi over 4 is just 1. Okay, so what does this equal? So when I square that, I get a half. 1 divided by half is 2. 2 plus 1 is 3. Okay, now let's use our trusty formula. Y is minus y1 is equal to mx minus x1. This gives me y minus pi over 4 is equal to minus 6 is the gradient, x minus 3 is the x-coordinate, times everything through by 4, gives me 4y minus pi is equal to minus 6 times x times 4 is minus 24x, minus 6 times minus 3 is positive 18, times by 4 is 72. Okay, that looks good to me, so let's just rearrange to make everything positive, and that gives me 4y plus 24x is equal to pi plus 72 as required. Brilliant. Okay, we have the value of a computer system in hundreds of pounds. Absolutely highlight that straight away because I know that's going to mess me up if I don't. Seen so many differential equation questions completely ruined because the units weren't considered. T years from when it was new is depreciating at a rate proportional to its value cubed. Okay, so what does that mean? That means that it's depreciating, so it's dv by dt, its change in value with respect to time, is proportional to negative, because it's depreciating, its value cubed. So using proportionality rules, that means dv by dt is equal to minus k v cubed, where k is the proportion, the constant of proportionality. Okay, this is a differential equation, so I'm going to want to separate my variables. So I'm going to first multiply by dt. So I now know that I want all of my non-v terms on the right and all of my v terms on the left. So dividing through by v cubed gives me 1 over v cubed dv is equal to minus k dt. And then, now that the variables have been separated, we can integrate. So the integral of 1 over v cubed, we can write that as a negative power, up the power, so that changes to negative 2. Divide by the new power is dividing by minus 2, which is the same as timesing by negative 1/2. And that is equal to the integral of k. Well, k is a constant, so that just integrates to, in this case, minus kt. And then I can put the constant of integration on that side. Don't need to put it on both sides. Just one side is fine. Okay. Right, so now would seem like a good time to then substitute in our conditions. So it says that the value of the computer system when it is new, so that's when t is equal to 0, was £1,000, which is actually 10 in our model because we're working hundreds of pounds. So that means that minus 1/2 times by 10 to the minus 2 is 1 over 100. K is 0, t is 0 because this happens when it's new, so that equals c. So that means c is equal to minus 1 over 200. Okay, great. So we can now rewrite this. Well, I can see here this is 1 over v squared, so rather than writing it as a negative power, I can write it as this. We still need to times it by negative 1/2 though, which we can sort out later. And that is equal to minus kt minus c, which is 1 over 200, or negative 1 over 200. Okay, let's times through by minus 2 now, which will leave this, and it will give me 2kt, and it will give me plus 1 over 100. Okay, now what we can do is we can say that our constant 2k, we can just label it a different constant. Why not? Let's just label it capital A, which we absolutely could do because, again, we've just defined that as a constant. We don't know exactly what the constant value is yet, so rather than just calling it 2 times something, we can just call it one lot of something else. So that is capital A t plus 1 over 100, and that is as required. Fantastic. Okay, let's just grab some space and then let's crack on with the next one, and that is asking me to, given that the value of the computer system halves after 1 year, find the value of t when the system is worth this. So the computer system halves, the value halves after 1 year. So that tells me that when t equals 1, v is half of what it was before, so half of 10 is 5. Okay, so let's sub those conditions in. So that's 1 over 25 is equal to 1a plus 1 over 100. Okay, so the 1 over 25 is the same as 4 over 100 minus the 1 over 100. That will leave me with a. So that tells me that a is equal to 3 over 100. Okay, so now we've got a model, we've got a complete model now, which is 1 over v squared is equal to 3 t over 100 plus 1 over 100. So we can write that, simplify that as 3t plus 1 over 100. Okay, great. So it says find the value of t when the system is worth £250. Again, this is why I highlight this. That means that it's worth 2.5. Okay, so we have 1 over 2.5 squared is equal to 3t plus 1 over 100 times through by 100. 2.5 squared is 6.25, and that equals 3t plus 1. So from here we can just do this on our calculator. So we can minus 1, and then we can divide through by 3. And let me figure out what that is. Okay, it gives us perfect 5. Lovely. Great differential equation question. Let's go. Okay, question 11. Use a suitable integration to show that bloody equals ln of 27 over 4. Okay, so suitable integration. Well, right now I'm looking at 1 over x, and that seems to me like the problem piece. And also, if I were to use that as a substitution, this would simply be u squared, that would be u cubed. So I'm going to go with u is equal to 1 over x as my substitution, and hope for the best. Right, so let's, I could rewrite that as x to the minus 1, might be helpful, might not, not sure, let's find out. First thing I always do is du by dx. So du by dx will be derivative of x to the minus 1, which is minus x to the minus 2. Okay, so du by dx is equal to minus 1 over x squared. We want to make x the subject, dx the subject, sorry, and we really would ideally like it in terms of just u, which we can do actually, because du by dx now, we can see that, like I said before, that if u squared is 1 over x squared, just because the substitution u is equal to 1 over x, so square both sides, we get that. So this looks like it's minus u squared. Now rearranging, because I want to get dx as the subject, gives me that dx is equal to minus du over u squared. Okay, great. Next thing I like to do is my limits. So draw a little table, put x here, put u here. So the first limit is 1 over ln 2. Now u is just the reciprocal of x, so nice and easy, ln 2. And 1 over ln 3, well again it's just a reciprocal, so ln 3. Okay, right, I think we are just about ready. I guess the one other thing I would say is that u cubed is equal to 1 over x cubed. Again, that could be useful. So let's go. Let's rewrite this integral. Our new limits are ln 2 ln 3. And we have u squared is 1 over x squared plus u cubed. And we are multiplying by e to the u. And the x is minus du over u squared. Okay, well, let's divide by u squared into this bracket to cancel that, and let's also take the minus outside. So dividing through by u squared is going to give me in this bracket 1 plus u, e to the u, du. Okay, great. Now there's a minus outside, and we can swap the limits over, and that just gives us the negative of the integral when we swap the limits over. So I can just get rid of that minus by swapping the limits over, which is always just a nice little trick to do. Okay, when I expand this out, I get e to the u plus u e to the u. Right, so what is this going to integrate to? Well, e to the u integrates to e to the u. This one we're going to have to do by parts. And I'm going to use the DI method because it's so quick and so efficient if you know how. So you write DI at the top. You just draw a little table like this. And you start along the side with a plus, then you go minus plus, and then minus if you need to. You can keep going down. We put the polynomial will go in the derivative part, and this case the other function is an exponential, so that will go in the integration part. So differentiate u gives me 1, gives me 0. So when I differentiate first time I get 1, when I differentiate again I get 0. And when I integrate it just gives me e to the u every time. So integration by parts, all you need to do is just follow this wavy pattern down. Like that. So that means the first term is u e to the u. It means the second term is minus 1 times e to the u. So that's just minus e to the u. And the last term would involve a 0, so that's just going to cancel out to nothing. So we can stop there. And that's between ln 3 and ln 2. Okay, great. So we'll look at this. Just cancel, cancel. Brilliant. So the integral is going to equal when it's evaluated. So we have ln 3, and then e to the ln 3 minus ln 2 e to the ln 2. Now when we have e to the ln of something, it's just equal to that something. So that's 3. So we've got ln 3 here multiplied by this, which is 3. So that's going to be 3 lots of ln 3. And by exactly the same token, this is going to be 2 lots of ln 2. Now we can take coefficients of a ln. We can raise that to the power of the input. So using our log rules, this is ln of 3 cubed, which is 27. And this is ln of 2 squared, which is 4. And then the final piece of ln rule is that when we subtract 2 lns, we can write it as their inputs divided by one another. Ooh, that was great. Loved that. Okay, final question. The showstopper, 14 marks. Woo! A curve lies entirely above the x-axis and has parametric equations. Yada yada yada. The finite region R is bounded by the curve, the x-axis, and the straight line with equation x equals a half. Use parametric integration to find the area. Wowza. Okay, so the first thing we need to do is figure out what this curve looks like. So what I could do is substitute in, well, t equals 0 is something which we should inspect first, because I know that gives me x equals 0. And tan of 0 is 0 as well, so it gives me y equals 0. Okay, so I know it goes through the origin. Okay, so it's going to go through that point there. We're saying x is equal to a half. So let's say a half is here, so that is going to be our boundary line from where we're integrating to. Okay, and we also know that the curve is entirely above the x-axis. So it's going to look something like this, essentially. So what we need to do is we just need to integrate between, well, this point here, which is t equals 0, and we need to find the t value for when x equals a half. So we can do that when x equals a half. That tells me that a half is equal to the x coordinate, which is sine squared t. Square root both sides gives me 1 over root 2 is equal to sine t. And that tells me that t is equal to pi over 4, because I know that sine of pi over 4 gives me 1 over root 2. Okay, and also t is between 0 and pi over 2. So yes, it can't be the negative version of that when we square rooted. So it has to be this pi over 4. T is pi over 4. Brilliant. Okay, so right here, t is equal to pi over 4. So that's what we're integrating between, those two t values, and we're going to get this area which we've been asked to find. Okay, now we can do our parametric integration formula. So we're going to be integrating between pi over 4 and 0, and the formula is y dx by dt dt. Okay, so let's substitute in y, which is 4 tan cubed t, dx by dt. Okay, that's the derivative of sine squared. So let's do it over here. So if I have sine squared, then I use what I call the bracket rule. It's the chain rule. The 2 comes down to the front of the bracket stays the same. We drop the power down to 1, and then we times by the derivative of the bracket, and the derivative of sine is cos. So we get 2 sine t cos t dt. Okay, so the 8 can come out because 4 times 2 is 8. We've got tan cubed. Well, tan cubed, I'm just going to use this area for a little working here. Tan cubed is the same as sine cubed over cos cubed, and then we're timesing that by 2, or not 2, we've taken the 2 out, so the 8's outside now. We're just timesing that by sine t cos t. So we can divide, well, we've got a cos there and cos cubed on the bottom, so that's going to give me cos squared on the bottom, because that cancels with the cos there. And we've got a sine cubed times by a sine, which is going to give me a sine to the 4. So this is the same as sine to the 4t over cos squared t. Okay, that can be written now as, well, sine to the 4, if I can convert that into coses, then we can cancel out some of the coses and hopefully get something easier to integrate. So sine to the 4 is the same as sine squared squared, and sine squared is 1 minus cos squared. So sine to the 4 is 1 minus cos squared squared. Okay, so let's now expand this out. On the top we get 1, and we're going to get minus 2 lots of cos squared t, and we're going to get plus cos to the 4t. And again, that's all over cos squared t. Okay, and now what we can do is we can split up each of these fractions. So the first one, 1 over cos squared, is the same as sec squared. And then we've got, that's just minus 2, because cos squared over cos squared is obviously 1. And then cos to the 4 over cos squared is cos squared. Okay, right. Now we still need to do some rearranging before we can integrate. This is one of those questions where you can just like use up a whole pad of paper. Okay, so cos squared. Okay, so we can't integrate cos squared directly. We need to use a trig identity. So back over to my drawing board over here. And the trig identity that we use all the time for integration is cos 2t. Because cos 2t, we know from our double angle, is equal to 2 cos squared t minus 1. Amongst other things, of course, it's 1 minus 2 sine squared, and it's also cos squared minus sine squared. But this is the one we're going to use, because we can add 1 to both sides. And then we can divide by 2. So we get a half cos 2t plus 1 is equal to cos squared t. Okay, so that goes into there. So that is plus 1/2 cos 2t plus 1/2. And we've got minus 2 plus a half here. So that's the same as minus 3 over 2. dt, which I've missed out every time. Please don't be upset with me. Okay, right, more space needed. Okay, so 8 goes outside. Sec squared integrates to tan, because tan differentiates the sec squared. Minus 3 over t will go, minus 3 over 2 will go to minus 3 over 2t. And cos 2t, well, cos integrates to sine. We keep the input the same, but we divide by the derivative of the input when we integrate. So we're dividing by 2, so it becomes a quarter. And that is pi over 4 and 0. Okay. Tan of pi over 4 is 1. This will give me minus 3 pi over 8. And pi over 4 times 2 is pi over 2. Sine of pi over 2 is 1, so that's just plus a quarter. Okay, and then when we sub in 0, or tan of 0 is 0, that will be 0, and sine of 0 is also 0, so it's just the upper limit which we need to consider. Thankfully. Okay, so 1 plus a quarter is 5 quarters, times by 8 is 10, and 8 and the 8 will cancel, so it's minus 3 pi. Beautiful! Well, I really hope you enjoyed that. If you did, drop a like, consider subscribing, and I will see you in the next one. Bye for now.